we talked about when we have a function of two variables, how do we find critical points? So a critical point of a function is either the point so that the f dx and the f dy both equal 0, or one of them does not exist at that point. All right. So the critical points are important because they are candidates for local extremums, meaning local minimum or local maximum, right? Okay. So if I have a surface like this, like a paraboloid, you can see this is a local minimum. If I have something that looks like this, then I have a local maximum here, local maximum here, for example, right? Okay. And this point is actually also an interesting point. So along this direction, you can see like along this curve, it's like a local maximum in this direction. But if you look at from the other direction, now you have this point as a local minimum, right? Okay, so this kind of point has a name called a saddle point. So it comes from the saddle used on a horse, but I figured that I don't know. I've never really seen a saddle in my life. But if you get potato chips, the shapes of potato chips look like a circle. Sorry, not like a saddle. Okay, so think about this. If I cut this piece out, okay, and I redraw it on the side, okay, put it on the side. So what I have is something that looks like this. Okay. So if it's a little hard for you to see, go get a can of pickles. You will see each of those chips will look like this. Okay, and you can see that from one direction you have the point in the middle looks like a minimum point, and from the other direction the point in the middle will look like a maximum point. So that's what a saddle point is. Okay, so personally I like to call it potato chip point, but that's not a real name in mathematics. In mathematics we stick to saddle point. Okay, so potato chip point is just my personal opinion. Don't use that on your test. All right, so let's assume we have function f that is continuous and has continuous partial derivatives. What does that mean? That means after you take the partial derivatives, both derivative functions are continuous. Okay, so just to think about, you have a function that is nice and smooth. So we don't have to worry about the case where derivative is not defined at a certain point. Okay, so now I have a critical point, AB, so that the f dx equals 0 and the f dy equals 0. Now I'd like to consider a function like this. Okay, so first of all, I consider a matrix formed by second derivatives. So it has an order, so the order is important. Df dx, fxx and fxy. So basically this is derivatives of the first derivative, so x and y. So that's what you have for the first row, and the second row is the derivatives of the second first derivative. So that's for df dy. So then again we have x and y like that. Okay. All right. So this is a 2 by 2 matrix. fxx, fxy, fyx, fxx. Okay? So this, it has a name. It's called Hessian of f. Okay? Hessian of f. So this is a 2 by 2 matrix. Each of the components is a second derivative function. Can be a constant, but in general it is a function, okay? And then we take the determinant of this 2 by 2 matrix, okay? So let me erase this. Let me erase this. I just want to give you a way how we form this Hessian matrix. Okay, so once I have a 2 by 2 matrix, the determinant of the 2 by 2 matrix is this. So you multiply the terms along the diagonal minus the product of the terms along the off diagonal direction. So that would be fxx times fyy, then minus fxy times fyx. All right. So when we introduce the higher order derivatives, I mentioned that in general, the derivative orders, they mirror. Whether you differentiate x first and y later or the other way around, they mirror. However, when f has continuous partial derivatives, they are the same. So these two are interchangeable. So in this case, we can just really think we are doing this. Okay? So this would be the determinant function of the Hessian of f. Okay? Now, you're gonna evaluate this determinant function at the critical point. Okay? So here's the important part. If the determinant at AB is positive and the xx at AB is positive, so this tells you the surface locally it opens up. So therefore, this point will give you a local minimum. Okay, so this says f of AB, that value f of AB is a local minimum value. Similarly, if the determinant at AB is positive, but this time the second derivative of x at AB is negative. So negative here means opening downward. So you can see locally it gives you a maximum point. So here we have local max at AB. Okay, so that means f of AB gives you a local maximum value. All right, so imagine if the function f represents the profit that you can get, then the profit at AB will be local max profit. Okay. However, if the determinant at AB is negative, then this point on the surface, so you have x, y, z, the point on the surface, will be like a saddle point like this. Okay, so along one direction it's like a minimum, along another direction it looks like a maximum. So this type of point is the so-called saddle point. So you have a saddle point like this on the surface. Okay. Last, if the determinant at AB is equal to 0, you know nothing. The test is inconclusive. Okay. So that way you will know that you probably will need to find another approach. Okay, basically you cannot draw any conclusion using the so-called second partial derivative test. This is very similar to the second derivative test that we have in Calc 1. We use the second derivatives of the function to figure out whether we have a local mean, local max, or maybe the test is inconclusive. So either situation could happen. Okay, but this is just a little more complicated. Be careful. Okay, keep this in mind. This is the test we have for testing local extrema.